Good afternoon, is Reid from University of Texas at Austin, and his title is The Arithmetic of Dehn Surgery Points.
Thank you, Alain, and thanks to the organisers for inviting me to the conference here. It's been great so far. It's great to be back in Cambridge. It's been the first time since a very long time since I've been here. So let me just begin by saying this is joint work with Ted Chinburg and Matthew Stova. And I'll get to some of the motivation and what the motivating problem was for this work shortly. And I'm going to do some live deforming and approximating on stage very shortly. But let me begin by saying a few words about some key players here. So the key players today are going to be finite volume hyperbolic three-manifold. So M H3 mod gamma is going to be finite volume, and by that I mean it's complete and orientable finite volume. So gamma here is a subgroup of PSL2C, and really throughout the whole talk today I'm going to abuse the difference between SL2C and PSL2C simply because I'm a man of matrices, and somehow 2 by 2 matrices are much more my thing. So we'll often just abuse the P in PSL2C. Okay, so there are two flavors to focus on. There's finite volume and non-compact, and there's finite volume and there's closed. And so for the purposes of today's lecture, the finite volume non-compact example, there's maybe two examples you should have in mind throughout the whole talk. I'll give you one now. And the non-compact guy, it should be something like this. So you take the complement of the figure 8 knot. So this is a knot K that's living inside the 3 sphere, and S3 minus K is hyperbolic. So it looks like H3 mod gamma. And in the case of the figure 8 knot, in the case of the figure 8 knot, then gamma is very explicit. Okay, so gamma looks like a pair of, it's generated by two meridians, and so they look like two parabolic elements, 1, 1, 0, 1, and where this omega here is a cube root of unity. So omega squared plus omega plus 1 is equal to 0. Okay, so that's kind of the example you should keep in mind throughout the rest of the lecture. There'll be one other non-compact example, perhaps two, that you should keep in mind, but this is the one that, you know, almost invariably at every talk I give, this example shows up. Okay, so what about closed examples? So there's oodles and oodles of closed hyperbolic three-manifolds. That's kind of what Thurston tells us. And one way that one might think about constructing this, again from the point of view of today's lecture, is that we can perform Dehn surgery on this knot. So we can view, so this is a knot complement, it's a non-compact manifold, but we can chop off the cusp, or in this case remove the interior of an open tubular neighborhood of the knot, and view the closed guys as coming from Dehn surgery. So we can think of this schematic for the compact version of this. So we chop off the cusp, and we've got a manifold with torus boundary, and so there's some topology that goes on in here. And by Dehn surgery, we're going to do the following. So over here is a solid torus V, and here is a meridian disk on this solid torus. And what we're going to do is we're going to choose our favorite essential simple closed curve, and I don't really care about the orientation of that. So maybe it's this guy here, so we'll call this guy R, and we're going to construct a new three-manifold, we'll denote by KR. And what we're going to do is glue this solid torus V onto this manifold with torus boundary in such a way that this meridional disk here, the boundary is glued to this R curve here. Okay, so we get a closed three-manifold now, for which we've kind of killed this R curve by gluing on that disk. So this is a result of the Dehn surgery, and Thurston says that for all but finitely many R, KR is also hyperbolic. So those are kind of the closed manifolds I want you to think about in today's lecture. Now, associated to these finite volume hyperbolic 3 manifolds are two very natural invariants that come, well, one is natural, one is at least natural in my office, which is not to say that it's natural for everybody else, but associated to gamma, this guy that's giving us this hyperbolic 3 manifold is the trace field so this is the field generated by the traces of the elements inside gamma. So again, if we were in PSL2C, that's just defined up the sign, but you know that's okay. So we take the field generated by this, and it's a consequence of rigidity. So that's not mentioned in the title of the lecture, but I'm told it's implicit. So you know, rigidity gets mentioned. So rigidity says that that this field, let's just call it K for the sake of it, K sub gamma, that K sub gamma over Q is a finite extension, i.e. it's a number field. So that's a very beautiful invariant. So if we go to the figure 8 note here, well, there's no prizes for computing the trace field of this guy. I mean, it's living inside matrices with coefficients in Q adjoin omega, and that's a degree 2 extension of the rationals. And it can't be any smaller, okay, because we can see omega as a trace, up to maybe 2. So the trace field of this guy here is just Q adjoin omega, which is just Q adjoin root minus 3. Okay, so that's an invariant of the manifold, again by most of rigidity, and it's surprisingly powerful in many interesting ways. So for example, one can rule out certain phenomena like totally geodesic surfaces, or proving the existence of, you know, closed hyperbolic 3 manifolds, all of whose closed geodesics correspond to hyperbolic elements that are not purely real, so they always have holonomy along the axis. Another invariant associated to this is a quaternion algebra. That I'll call A sub gamma. So how is this constructed? So this is constructed in the following way. We take all finite sums, AI and gamma I, where AI belongs to the trace field, and gamma I belongs to gamma. So as it stands here, this is just some mess. Okay, now what is a quaternion algebra? Well, this is a 4-dimensional central simple algebra. And it's not too hard to prove that indeed that, you know, this guy here does satisfy the properties of being 4-dimensional, central, and simple. So 4-dimensional, you can almost see quite quickly with a mild bit of thinking. If you give me any alpha and beta inside gamma, such that alpha and beta don't commute, then you can think of just taking a basis, 1 alpha beta and alpha beta for something. So you take K combinations of these guys. Well, in fact, if you take C combinations of these guys, because of this condition here, this actually generates 2x2 matrices over the complex number. So you get M2C. So it's even 4-dimensional over M2C, and basically that's why this whole gadget here turns out to be 4-dimensional. And again, there's a little bit of argument to prove that these are central and simple. Okay, so you get this quaternion algebra that's associated to the gamma. Now, I can tell by the looks in your eyes, you're really just not impressed by the fact there's a quaternion algebra associated to gamma. But I can tell you this, and you'll see more about this later. It's very, very powerful invariant associated to a hyperbolic 3 manifold. So to give one example, and we'll see some more examples shortly, there's a construction of towers of rational homology 3 spheres, i.e. there's closed hyperbolic 3 manifolds which are rational homology 3 spheres, and you can construct a tower of finite index normal subgroups that descends to the identity, all of which are rational homology 3 spheres. And the only known constructions of such things go about using properties of this quaternion algebra over the number field. There's other examples. One can also say constructions of closed hyperbolic 3 manifolds, all of whose closed geodesics are simple, comes from constructions of quaternion algebra with certain properties. So it's a very powerful invariant. So what's the associated algebra to to the figure 8 knot, well, again, there's almost no prizes for guessing this. We're inside 2 by 2 matrices with coefficients in Q root minus 3, and so that's the natural kind of condition here. One thing to notice that, when you are a knot group, a hyperbolic knot group, you always have this parabolic element you can conjugate so that your favorite 1, 1, 0, 1 is in there. Well, what do parabolic elements correspond to? Well, parabolic elements, they give you 0 divisors. Okay, so if you just look at 1, 1, 0, 1 minus the identity, that is 0, don't tell me 1, 0, 0. That's a 0 divisor. So in fact, what's the only possibility for the algebra associated to any hyperbolic knot group? It's always 2 by 2 matrices over the rationals. Okay, there it is, back again. Okay, I'll say a little bit more shortly about these other kind of quaternion algebras that arise, but now I'd really like to endeavor to deform and approximate. Okay, so what do we mean by that? Well, let me just get out of here and with good luck. Oh, there we go. A little pop-up ad for the audience. Okay, so what I'm going to do is use this program snap, and this allowing us to kind of deform the hyperbolic structure in the figure 8 knot and realize these Dehn surgeries on the figure 8 knot and understand something about the trace fields and these quaternion algebras. Okay, so for those of you that don't know Snap is this rather fantastic package that was developed by Oliver Goodman, Walter Neumann, Craig Hodgson, perhaps one other person in Melbourne. And what they did was they took Snappy, this amazing program that goes back to Jeff Weeks, that's kind of numerical, gives you approximations to things that are algebraic. And then what Snap does is they take Paris, and they take various packages from Paris and meld them into this great program called Snap that allows one to kind of use algorithms like LLL to replace approximate algebraic numbers by algebraic numbers. So let's do the following. So so again, Snappy and Snap, they have these huge sensi of hyperbolic three manifolds given in various ways. So the first thing I'm going to write in here will make some sense to some people. So there's a census of 5 tetrahedra. So this is manifolds that one gets, non-compact hyperbolic three manifolds that can be constructed by gluing together 5 ideal tetrahedra in hyperbolic space, and the number 4 refers to the 4th guy in the list. And by good fortune, this turns out to be the figure 8 knot. So that's its volume, and we all know that, of course. Ho ho. It's a knot complement in the 3 sphere, so homology is Z, and so that's good. And so now we want to start looking at what we do when we do Dehn surgery. Okay, so this slope R, I'm going to give coordinates that involve a pair of rational numbers to parameterize these slopes. So let me just take one of my favorite ones. So I'll surge in the manifold 5, 1. Okay, so Snap says the solution is geometric. I'll print the volume just for excitement's sake. It's 0.98, and for those that might know about these things, it's the second smallest volume of a closed hyperbolic three manifold. And let's try. I could try, but I've failed miserably in the past on this, Ian. Sorry, let's just see if Is that better? Go on. Is that better? Okay, thank you. Right, so that's the volume, and now we can do things like compute the trace field. Now I'm going to do something that says co-in. So there's something called the invariant trace field, and I'm not going to sort of get into that here and worry about the difference between the trace field and the invariant trace field. For this particular manifold that I've computed, 5-1 surgery, the trace field is the invariant trace field. And the reason for that is the homology is finite and it's got odd order. Okay, so again, there's sort of niceties here that we need not concern ourselves with. But what we want to know is, well, look at this. There's the trace field that says degree 4 extension of Q, and it's got 2 real embeddings, that's what the 2 stands for, and 1 pair of complex conjugate embeddings, and that number there is the discriminant of the number field. Okay, so what about this algebra that you may or may not care about? Well, I do, so we're going to do it. So this tests for arithmeticity. So the P-arith is now going to test for arithmeticity. So let me just try to explain a few things here about what this means. So what does real ramification mean? So when you were small children, the first quaternion algebra that you likely heard about was the Hamiltonians over the reals. So over the real numbers, so over R, there are two quaternion algebras. There's the Hamiltonian quaternions and the 2 by 2 matrices over the real numbers. And if your number field has got a real embedding, you can ask, well, what happens to that algebra at the real embedding when you tensor up over the reals? Either one of two things can happen. Either you get this or you get that. And this is the case where the word ramified appears. Okay, so ramified means you get the Hamiltonians at these places. Now, what does finite ramification mean? Well, again, we need not concern ourselves too much about that, but let's just think about the p-adic rationals. It's a similar case. There's two isomorphism classes of quaternion algebras over the p-adics. There's M2 of QP, and then there's some division algebra. There's a unique division algebra over the p-adic rationals. It's a bit like the Hamiltonians. So the finite ramification in this case is none. Okay, but in this case, you know, pay attention to the word none. That's going to be important. So let's do a few more. Okay, so here is another guy. I'm going to do a half surgery. And I know already that because this is an integral homology sphere, that if I compute the invariant trace field and then test for arithmeticity, I know I'm going to get no finite ramification. Okay, so I just knew that because there is a theorem that if you're an integral homology sphere, this algebra cannot have any finite ramification because that gives rise to finite abelian quotients. Okay, so that's another case where you get information from the nature of the quaternion algebra. And notice in this case, the field has got this signature, as it's called, 5, 1. So there are 5 real embeddings here and 1 pair of complex conjugate embeddings. And notice that 2, 3, 4, 5 show up as being ramified, i.e. you get Hamiltonians, and 1 doesn't. So at 1 you get M2R. So in that case, what this is really saying is that, well, if you think about that for a minute, this is giving you either an SL2R representation, in the case when you've got M2R, or an SU2 representation when you have the ramified case. Okay, so let's go on. It's just so, oh, that's not right. Flat. Yeah, you don't want to see flat. So we know there are lots of non-hyperbolic surgeries in the figure 8 note. So let's start that again. 5,4. SU 9,1. So we'll do the same again. Let's compute the field. So you get this degree 7 extension. And let's test arithmeticity. And in fact, you'll see in this case, well, what does that mean? Finite ramification blank. Finite ramification says this 2 together with some garbage here. Well, forget about that. It just says there's a prime ideal in this number field that lies above 2 in this extension. So the only prime involved here that's interesting from the point of view of ramification is 2. And the real ramification we see is 1, 2, 3. So again, you get SU2 and SL2R representations coming from these surgeries. So let me maybe just do a couple more. So once again, you see that 2 is involved, and maybe just do one more for the sake of excitement. SU 7,1. And in this case, again, you see none. So the thing to take away from this modest experimentation here is that the only things you see are 2 or none. Okay, that's the thing you should take away from this. So what I'd like to do is give you another example where things are a little different. And so the figure 8 note has appeared. Now, coming from Austin, small children walking the streets know that the most famous knot in Austin, apart maybe from my office, is the -237 pretzel knot. And I'm not going to draw it, but I'll maybe, because there are experts in the room. So this is -2 twist here, and then there's 3 here and 7 here. So the -237 pretzel knot is kind of a famous knot for all sorts of reasons that we're not going to get into here. But let me tell you what number this is. So Reid's census 5, 16. So this is again constructed from 5 tetrahedra, and it's number 16 on the list. Let's check the volume. And you see it's that, and let's check its invariant trace field. For knots, in fact, the trace field is always invariant trace field. So we see here that it's a cubic field. So already we deduced that for this minus 237 pretzel knot. Yeah, Rich?
I thought the figure 8 was constructed from 2 tetrahedra.
It is. 5 is the kind of max on this list. So this guy's actually constructed from 3 tetrahedra. Figure 8 knots 2, but it's up to 5 tetrahedra. Right, thanks.
Oh, okay.
So already you see, in this case, because we're in a matrix algebra, it turns out we have to have an SL2R representation that comes from this construction here. So let me just sort of convince you. So the minus 237 pretzel is interesting for many ways. And if I can find it. Yeah, so let's do this. So one of the ways that it's interesting is that it has a lens space surgery. And here is the lens space surgery. You do minus 1, 1 in this particular coordinates, and you see a cyclic group of order 19. And so by Perlman, we know now that that's a lens space, but of course we knew it was a lens space by other means in this particular case. But anyway, that's not germane. It's just a check for those in the audience that know the minus 237 pretzel. Okay, so let's see what we do here. Let's do this guy. So we do minus 3, 1 surgery. We compute the invariant, we compute the trace field in this case again. And then we check arithmeticity. Now, immediately in this case, we see that 13 shows up. So that was something that was very unusual from the perspective of the figure 8 knot, where we always saw none and 2. And let's do SU 5, 1. So in this case, we can get this degree 13 extension, and we'll check arithmeticity again. And in this case, we see 5. So let me just do one more. So let's do minus 3, 4. So you get this degree 7 extension. And arithmeticity, well, here in this case, the finite ramification shows up as something of 149. So already we've seen in the case of minus 237 pretzel knot that there's a very different kind of phenomena, albeit based on a very small and limited amount of experimentation in this kind of Dehn surgery space. But as you can see, this 149 shows up very quickly in this game. Well, time is moving on. So I was going to do one more example, but perhaps I won't. Well, perhaps I will. It's just so we'll do one more example. This is number 130. Sorry, Reid census 5137. So this is a great example, and one of the reasons it's great, it's trying hard to be arithmetic, but it isn't. So the trace field is the right kind of field for an arithmetic guy, but it isn't. So you get this example that has the same trace field and the same quaternion algebra as an arithmetic guy, but it isn't. And it says integer traces, no. So that's why this guy is not arithmetic. Now the reason that I like this guy, it's not a knot in the 3 sphere. It's a knot in S2 cross S1, but its homology is just Z. And in fact, in this case, maybe I won't do any examples here. In this case, if you begin to experiment, you only ever see none as the possibility for the ramification set, for this finite ramification set. And so this talk is going to basically be about ideas and trying to explain this phenomena that kind of I observed kind of some time ago and never really had a sense of why such a thing should be true. And what I hope to do is really talk a little bit about some of the background as to explaining this this kind of picture of these experimental results, and also state a theorem, discuss some of the ideas that relates to sort of classical knot theory, the Alexander polynomial, and then at the end of the lecture related to more kind of contemporary mathematics and low-dimensional topology that's kind of remarkable, and maybe it's just coincidence and maybe it isn't. It's the world of the Hegardt floor machine. I only said that without blushing, and I know there's experts here, but anyway, we'll get to that later. Okay, so let's go back and get started on this. Right, so let me just set up some notation. Gamma is going to be the fundamental group of the knot K. If K is hyperbolic, then this surgered guy is hyperbolic for all but a finite number, and when it is hyperbolic, then we get gamma sub r to be the trace is the group. The trace field is K sub r, and the algebra is B sub r. And the Alexander polynomial is just going to be denoted traditionally by delta K of T. Okay, so the theorem that Chinburg and myself and Stover proved is the following. And so what it says is the following, that it's an explanation for what one sees experimentally here. Namely, if you've got a hyperbolic knot and you know the Alexander polynomial satisfies this condition star, and let's not worry about what it means right now, and we probably won't worry about it when it means later. But anyway, it's up there. It's a condition on the roots of the Alexander polynomial. So W is a square root of Z. Then you get, and you want this equality of fields. Q of W is Q of W plus 1 over W. Then you can really say there's just a finite set of rational primes for which any prime that ramifies the algebra B sub R has to divide one of these rational primes. Okay, so this is meant to help explain what we saw in the cases of the experimentation. Okay, so the key thing to remember is this star. It's a condition on the roots of the Alexander polynomial. All right, so when delta kt is 1, then this S is empty, and BR is ramified at all finite places. So that example 137, even though it was not a knot in the 3-sphere, its homology is Z, H1 is Z, you can compute its Alexander polynomial, and miraculously it's trivial. And so in this case, it's unramified at all finite places. That's really what the experimentation showed, and this is the reason why it's true there. So for the figure 8 knot, which is the one that maybe we like the best, or not if you're from Austin, the Alexander polynomial is this guy. So the roots are 3 plus or minus root 5 over 2. If you take square roots, you get this 1 plus square root 5 over 2. And if you take W plus 1 over W, you get root 5. So in this case, you know, Q of W is the same as Q of W plus 1 over W. So in this case, star holds. Okay, so that's trying to explain why. Now, it just gives a finite set, so we don't really know why. I mean, in the theorem it said none or 2. Those were the only things that show up. But in this case, sort of a deeper analysis, that's kind of a mod P version of the theorem that I stated above, one can actually prove that S is 2. So that really does explain why, in this case, you only ever see algebras ramified at 2. And in the case of the minus 237 pretzel knot, it's kind of rather splendid. So the Alexander polynomial for this guy is up to kind of a sign, the famous degree 10 polynomial of Lemma, that is the candidate smallest Mahler measure guy. And in this case, if you take Z to be a root and take W squared, W satisfies an irreducible polynomial of degree 20, but the W plus 1 over W satisfies this degree 10 polynomial. So star fails in this case. And in fact, as we'll see later, this also gives us the reason why you see infinitely many primes appearing. Well, I say infinitely many. You only saw 5 or something like that. But in fact, the theory that we'll talk about later gives you infinitely many different primes that arise in this way to construct these quaternion algebras. Okay, any questions or comments about that? All right, we're all on top of it, I can tell. Okay, so what's the setup here to try to understand these? Well, these Dehn surgeries that arise, they give you a homomorphism from the knot group onto the fundamental group of the Dehn surgered guy, and if they're hyperbolic, you then get a representation into SL2C. So a natural place to frame this discussion is representation varieties and character varieties. So I think many of us are fairly familiar with this. So if you've got a finitely generated group, you can construct the set of homomorphisms from G into SL2C. Just in the obvious way, you send a generator to a 2x2 matrix with determinant 1. You get coordinates. Relations give you matrix equations, and therefore this determines some system of polynomial equations in these coordinates, and these together with the determinant equations cut out some algebraic set defined over Q, and indeed it's defined over Z, and this is the so-called representation variety. Now, the thing about representation variety, it isn't sort of, you know, invariant under conjugation. So what you really want to do is pass to something that's invariant. So the character of a representation is just a function that goes from the group to the complex numbers that picks out the trace of rho of G. And the good news is the set of characters, and we'll do an example shortly, actually also has the structure of an algebraic group. Sorry, algebraic set defined over Q. And this is the character variety. And indeed, it turns out that you really only need finitely many characters to determine the coordinates of the character variety. So for example, if your group is 2 generator by A and B, then you just really need the character on A, the character on B, and the character on AB. And that gives you the character variety. And one way one might think about this is that the character variety, you might just think of modding out by the action of SL2C by conjugation. And that's true if the representations are irreducible. There's a mild irritation when the representations are reducible, i.e. Reducible means conjugate into upper triangular matrices. But for irreducible things, and these representations that come from Dehn surgeries when they're hyperbolic are indeed irreducible. So Thurston proves that if you have a one-cusp hyperbolic three-manifold, so in particular a hyperbolic knot, then there's a particular component that's picked out, namely the one that you see all these Dehn surgery representations. You do the Dehn surgery, you get this hyperbolic manifold, you use the representation there, that gives you this collection of representations and characters, and that picks out some component that turns actually out to be a curve component in the character variety. So curve meaning complex dimension 1, and we're going to call that the canonical curve. And this contains the character of the faithful discrete, I've got a pointer here so I can point, the character of the faithful discrete representation of the one-cusp hyperbolic manifold. So these character varieties and the canonical components have been fantastically powerful tools in the topology of low-dimensional manifolds. First, really pursued by Thurston, but really by Culler and Shalin, and then various members of the audience, Culler, Gordon, Lucky, Shalin, Boyer, Zhang, and many others, to really prove very deep theorems about the topology of three manifolds. One thing to mention here is that, again, one of the reasons we're trying to understand these quaternion algebras is that one really wants to understand something about the points on this curve that's the canonical component. All these Dehn surgery points have algebraic coordinates, so they give algebraic points on this curve. And so one wants to understand something about that. One wants to understand which curves arise. And perhaps kind of interestingly is a question that, it relates to the existence of when the algebra is ramified at a real embedding or unramified at a real embedding. So let me just preface the question by the following, that Kronheimer and Rofka, they prove that every, let's just say like every knot, non-trivial knot, has an irreducible SU2 representation. Now, what they don't do, and what's still open, so open finds such on the canonical component, and I don't know if I called it yet, so that's going to be x0. So find one of these SU2 representations on the canonical component, so that's open, and one might try to approach that using the structure of these quaternion algebras that arise from Dehn surgery on a hyperbolic knot complement to prove that you are ramified at some real embedding. Now, I wish I could say something meaningful about this, and we have some results that are stated in the paper, but they're not sort of things that one would say in polite company, and I'm just not going to say them because they're just not very interesting in comparison to the stuff we do with the finite ramification. So as I said, the canonical curve contains the characters of representations coming from hyperbolic Dehn surgery. So here's this canonical curve living there. One thing you might think about though is that if you're a knot complement, the first homology is Z. So there are many ways to map Z into SL2C. So you get this character of abelian representations that are somehow not as interesting as these guys. So these are reducible representations. And we'll come back to that shortly. So let's do an example here. So let's take the figure 8 knot and compute the canonical component right here. Now, my mathematical license expired, and I haven't been able to renew it yet. So I'll just do it here. So what do we want to do? So we want to normalize this. We're looking at components that contain irreducible representations. So what one can do is just conjugate so that rho of A fixes infinity and rho of B fixes 0. That's just an elementary conjugation. You evaluate the representation on the relation, and just for kind of mathematical reasons, WA minus BW is kind of easier to deal with. And you get this. So you get this polynomial and these two variables. So let me just point out here that A and B, these are meridians of the knot, so they're actually conjugate. That's kind of visible from the relation here. So the trace of A and the trace of B is the same under any representation. So the only two parameters one needs are the trace of A and the trace of AB to pin down what the character variety would be living naturally inside C2. Okay, so that's this equation. We need to convert to traces. So if we set z to be the trace of a and t to be the trace of ab, and then you pretend you do resultants in your head, and you get this. So that's a polynomial in two variables, z and t, that are traces, and you get this equation here. So it's an algebraic set that's cut out by this. So what we've just proven is that if there's an irreducible representation, then the characters satisfy this. Now, in particular, this is cubic, but there's a little bit more work to do to prove that this is really the whole of the canonical component. But if you do this little change of coordinates here, very quickly you see that you get to this part here, that this is y squared equals a cubic, and the cubic has got distinct roots. So in fact, this is irreducible as an algebraic set, and so we've just proven that the canonical component for the figure 8 knot is a genus 1 curve. In fact, it turns out that that's an elliptic curve. There's a rational point here. And I should also say that I'm just going to be completely informal about going between the affine world, the projective world, smooth, not smooth, singular points, no singular points. You know, you have to worry about such things, but just don't worry about them. You know, that's my advice. So in this case, you get a genus 1 curve. For the minus 237 pretzel knot, you do the same computation. Here, A and B are not meridians. They're just a pair of generators. You do the same argument, and as you see, you conjugate here. You do the same kind of conversion to traces. And in this case, you find that the coordinates are just rational functions of Q. So in this case, what we see is that, you know, P and Q, so we've got Q, you've got P and R as rational functions of Q. So in fact, in this case, the canonical component, at least the smooth projective model, is just CP1. So those are two sort of fine examples. Now, what about reducible representation? So we talked about these abelian representations, but there could be other reducible representations of the knot group that are more interesting. Well, let's take the figure 8 knot. So reducible representations, remember, are conjugate into upper triangulars. So we can take this thing here. So remember, the matrix, the second matrix was just something of the form x 0 r x inverse. So if we set r equals 0, this gives us a way to get reducible representations. And if you do that and stare at it for a minute, you see that a solution that's corresponding to a reducible representation looks like that. Now, the eagle eyes will have spotted that if you set x squared equals to t, this actually gives the Alexander polynomial for the figure 8 knot. And we'll maybe have time later just to quote the theorem of Dehn, that's kind of the standard framework for this, that reducible non-abelian representations of the knot group really correspond to roots or square roots of roots of the Alexander polynomial. Okay, so let me just make a couple of comments. For a hyperbolic knot, there are only finitely many characters of reducible representations on the canonical component. It's a standard fact. And if there is a character of a reducible representation, then you have to find the character of a reducible representation with non-abelian image on that component. And as I mentioned, the theorem of Dehn, so he basically, you know, saw the Alexander polynomial being cut out as a kind of a representation variety for the knot group into kind of the affine space, the affine group over the complex numbers. So there's a very close correspondence. So the takeaway is there's a very close correspondence between reducible representations and the eigenvalues of reducible representations and the Alexander polynomial. So if your Alexander polynomial is trivial, you have nothing to worry about from the point of view of non-abelian reducible representations. Okay, so the tautological representation. So what I'm going to try to build up to is, you know, how do we describe this theorem that I mentioned at the start? How do we see these quaternion algebras with this specified ramification behavior at certain primes? And to do that, we're going to work over sort of the function field of the curve. So the tautological representation is a bit of a mouthful when you first see it, but maybe let's go over here. So the way to think about it is this: if we think of the case of the figure 8 knot, we had x, 1, 0, and then let's just call that y, and where we have x, y equals 1, and then here we had x, 0, r, z, and you know x, z equals 1. And what the tautological representation is these are sort of functions now. Okay, these are just functions on the representation variety. So we can think of taking an element gamma in gamma and looking at what rho does to it. We expand out the word for gamma in these generators, and what we see is some polynomial in x, y, z, and r, poly. So we get a representation of the group gamma that goes into SL2 of the function field of something. So I haven't quite said what the function field is. It's not quite the function field of the canonical component. It's some finite extension thereof. I should say as well, I've put Q here just because I'm thinking everything is defined over Q. That's a slight lie, but not a big enough one to worry about. There are other bigger lies that you should be worried about. But anyway, that's kind of what the tautological representation does. It sends the group into SL2 of this function field. Now, in the same way that we built the quaternion algebra for a group gamma, so we've got this tautological representation that I'm calling P0. So this takes gamma into SL2 of some function field. And the thing to notice here is that the trace of this thing is just a character of rho evaluated on gamma. And now it turns out, again, it's kind of a simple exercise, that on the canonical curve, P0 is a faithful representation of the group into this SL2. And what we do is we just do what we did before. We take finite sums of things in the function field, so traces. So remember the last time we took, for the Kleinian group, we had finite sums of things in the trace field with elements in the group. Here we take finite sums of things in the function field associated with the canonical component and summed over images of the elements in the group under the tautological representation. And this is a quaternion algebra once again. It's one of these standard facts. And well, how do you describe quaternion algebras? Well, one way that one describes them is by the so-called Hilbert symbol. Now, this is a flabby way to describe a quaternion algebra. So what's your favorite Hilbert symbol? So if we take the Hamiltonians over the reals, then this can be described as the following symbol, -1, -1r. So this is meant to say that we have a base as 1i, j, and ij, where I squared is -1, j squared is -1, and I and j anti-commute, and ij squared is -1. So a Hilbert symbol more generally can be constructed where, you know, this is just saying I squared is some function, j squared is some function, and I and j anti-commute. So these are functions on the curve that allow us to describe a quaternion algebra over the function field associated to the canonical component. So this is going to be this universal object now that we're going to work with. So let me draw a schematic to try to explain what we're going to try to do. So here is x0. Now, so really this is, you know, thought of as the smooth projective model of x0. So it's just some curve. And, you know, on this curve, we see lots of interesting things. So here, let's call this chi rho 0. This is the character of the faithful discrete representation.
Yeah, it's not very.
What's that?
Don't use the red now.
Oh, okay. Okay, it's a big red blob there. Okay, so that's the character of the faithful discrete representation. And so we have Dehn surgery representations, and then here they are, suggestively drawn so as to somehow look like they're converging in some sense to the character of the faithful discrete representation. So these are characters. Now green on green, that's really naughty, so I'm not going to do that. So let me write it in white. So characters of Dehn surgery representations. Now maybe here's the blue. So blue, let's go blue dots. So these might be the characters of non-abelian reducible representation. So characters of non-abelian reducible representations. And then there's these x's. And what's x? X is a point at infinity. It's an ideal point. So this is a way that characters degenerate So we think of the affine case where you have these points at infinity where characters go off to infinity. So some functions, some trace functions are blowing up as they go off there. And these are the so-called, let's just call them points at infinity. So that's kind of what this character variety looks like. And so we have this algebra defined over the function field of the canonical component, and we have these functions that are describing a Hilbert symbol. Now you'll see that there's certainly places where this might be bad, in the sense that, well, there might be places, for example, the faithful discrete character, where that is 0. Now that's not such a good thing when you're trying to compute a Hilbert symbol. And there's places here that this might be 0. Well, when is this 0? Well, this is kind of the case when you get, well, maybe it's a parabolic element, this commutator, or it could be a character of a reducible representation. So characters of reducible representations are kind of characterized by the fact that the traces of all commutators are equal to 2 under the reducible representation. So there are things that come up here that, if you try to make sense of what this means, there are issues at certain points on this curve. And so what we need to try to do is come up with a framework for us to kind of take that Hilbert symbol for this quaternion algebra over the function field and make sense of what this tells us about these points. Okay, so now I can hit the light speed button because the word's Azumaya algebra. So the right framework for this is the Azumaya algebra framework. So what is that? Well, it's a generalization of a central simple algebra over a field to, well, you take a commutative local ring with a maximal ideal M and a residue field K, and you think of what that might mean, what a central simple algebra might mean if you just allowed a commutative local ring. Well, you say it's an Azumaya algebra over the ring if, well, it's a free of finite rank, there's an R module, and when you tensor up over the residue class field, you get a central simple algebra. And it's quaternion if the rank is 4. Okay, so what's that got to do with curves? Well, if you give me a point on the curve here, so here it is, some character. So you're in the function field. Function fields come equipped with valuations that tell us what the behavior of functions at given points are. Namely, there's a way of describing a valuation that looks at, give me a function in the function field, and you look at the order of the zeros, if there are any, the order of the poles, if there are any, or you just call it 0. So there's a way to define the valuation on this function field, or the localizations at points, and this allows us to define Azumaya algebras over a curve. So again, you probably don't really want to see much of this, but anyway, if you have this Hilbert symbol that we've got back there, it defines an Azumaya algebra over the curve if for every point on the curve you can get a quaternion Azumaya algebra locally, so that when you tensor up over the function field, you get back to the A that you start with. Okay, so it sees this kind of local behavior piecing together to give you global behavior. Now, for those that kind of understand these things, so what this is really saying, you know, sheaf is kind of the word that one should say here, and I'm not going to say it. There's a way of decomposing your curve into pieces, and on these Zariski open pieces, you construct certain sheaves that allow you to construct this Azumaya algebra in a more careful way. So I've got a kind of warning here, actual definition. You know, we don't need to see that. But the key thing is that the quaternion algebra given by the Hilbert symbol extends to this Azumaya algebra if and only if there's a certain condition involving the so-called tame symbol. And so the tame symbol is this class in the residue class field mod squares, and you have to go in and compute that. Okay, so that's the thing that's an obstruction to this local Azumaya algebra existing. Okay, so the point now is, let me just say a few words here, that it's a classical results from work of Harari, and perhaps even earlier than that, that when you do extend to an Azumaya algebra, there is this set as described that gives you either finitely many primes or you get infinitely many primes. Now, to get in there and prove, for example, in the case of the figure 8 note that the set is just a prime 2, that requires more work, but Harari does give you this finite collection. Okay, so what needs to be proven is that if this condition star on the Alexander polynomial holds, then you get an Azumaya algebra over the curve. Okay, so let's talk a little bit about that. So here's the Hilbert symbol once again, and again, we've mentioned previously that there are problem points when, you know, the trace of this guy is 2 or the trace of this guy is 2. Now the good news about a Hilbert symbol, as I said earlier, it's a very flabby object, so you can change bases for Hilbert symbols, and that kind of improves your life. So let's take a look at this. So suppose we've got a point on the smooth model, so x0 here, so maybe we're at this point here. So here's the point chi, and we're at a point here, so we're away from ideal points, so there's no worries about poles. Well, we might have had a 0, but in fact, let's assume we don't have a 0 for the function I sub g. Well, what does that mean? It means that the order is 0 at the point for both of these functions. Okay? There's no pole and no 0, so the only possibility for the order at that point is 0. So in the Hilbert symbol, when everything is 0, you just get 1. So that's trivial in this residue class field mode squares. Okay. So let's assume that we've got some character of an irreducible representations, and suppose that, you know, we can find a pair G and H so that the images of G and H do not commute. Now, when we have an irreducible representation, that is indeed the case. So we can change bases of this quaternion algebra to kind of work with this G and this H. Now, the point is here, so what does it mean for the tame symbol to be trivial? Well, what's, you know, if you think about what it means for a quaternion algebra to be trivial, okay, well, what it means is it's just a matrix algebra. Okay, so if you get the matrix algebra, you're trivial in the tame symbol. So in this case here, if this is equal to 2, then it turns out that this is parabolic because it's an irreducible representation. This commutator is not the identity. And in this case, the tame symbol is trivial because you find a parabolic element locally. So if you recall back, parabolic elements correspond to 0 divisors and hence matrix algebras. So that's why that is the case there. So we need to deal with points which are ideal points and points which are characters of reducible representations. And, well, you just have to sit down and do it. In fact, interestingly, it's the reducible representations that cause the most pain and suffering. So that's why this obstruction comes from the Alexander polynomial. So I'm not going to say too much more about this. The Alexander polynomial, as we discussed earlier, from the work of de Rham, corresponds to roots of the Alexander polynomial. So that's where this comes from. And so let me just zip on through here and go to the punchline. That basically one gets to the point where you see that the condition star is that you're forced to have something being a square. So it's trivial in the residue class field. Okay, that went too quick, but don't worry about it. You know, we can talk later. So that's kind of what you have to do. You just have to go in there and evaluate, compute this tame symbol at the various points, and the reducible representations are really the place where this causes the most pain. So what I'd like to finish with is this kind of comment I alluded to at the start of the lecture, that, well, you can find infinitely many fiber hyperbolic knots that are Azumaya positive, that satisfy this condition star. And you can write down a family of Alexander polynomials, for example, those ones. And these are Alexander polynomials of knots because, in fact, any polynomial that looks like this is the Alexander polynomial, for example, of some arborescent knot, thanks to the work of Stoimanov. But there are infinitely many guys that are not Azumaya positive. And in this case, it's, you can take a family that's a minus 2, 3n pretzel knots. So these guys here, their Alexander polynomials are a bit like the one for minus 2, 3, 7. They're related to Salem numbers. And you can kind of prove that Salem numbers have irreducible polynomials that never give you this condition star. And then there's twist knots, which are non-fiber typically. But you can show that, you know, half of them turn out to be Azumaya positive, i.e. condition star hold. So these are things that one can just compute. But what's perhaps most interesting is the following, that there seems to be an intriguing connection that you know, if K is a hyperbolic L space knot, is never Azumaya positive. So what does that mean? So an L space is a rational homology 3-sphere. I mean, Boyer's laughing at me now, but anyway, I'm going to say it anyway. It's a rational homology 3-sphere for which the Heegard-Floer homology has rank which is minimal, i.e. it's the order of the first homology group of the rational homology 3-sphere. So the Heegard-Floer homology, you get some abelian group, and it's just, you know, what the size of that, the rank of that abelian group. So that's what an L space is, and a hyperbolic L space knot is just a hyperbolic knot that has an L space surgery. So what's the favorite example, and this is why it's well loved in Austin, if you take minus 237, it has a lens space surgery. Now whatever L stands for, there's a fighting chance you're going to guess that it stands for, you know, something to do with length space, and you'd be right. So length spaces are L spaces. And we notice that minus 237 is not Azumaya positive. Now, moreover, in fact, all those knots Jn, the ones that come from the minus 23n pretzel knots, these are all L space knots. I forget who proved that. It might have been Oswald and Szabo, it might have been Tillman, and was it Toy and Allison, or was it Oswald and Szabo? I know. Yeah, okay. So these minus 23n knots, these are L space knots, I beg your pardon. And so they never, these polynomials we saw, they never satisfy condition star. And the knots Kn above, these are not L space knots. And why is that? Well, Oswald and Szabo proved that if you are an L space knot, the Alexander polynomial has some very special constraints on the coefficients of the Alexander polynomial. They can be 1, -1, or 0, with some additional construction that they have to satisfy. So, in fact, there are many, many more examples to support the conjecture that if K is a hyperbolic L space knot, it is never Azumaya positive, that this condition star should never hold. Now, it may well just be coincidence, but it seems kind of an intriguing connection between the world of the character variety in Azumaya algebra and the Heegard floor machine. So I think I'll just stop there. Thanks.
Thank you very much. Questions, comments? Yes?
Do you get a result in general when this star is not satisfied as well? Or you said that you get infinitely many primes for this.
Right. So you get infinitely many primes. Now, what we don't know is that, in fact, you can arrange infinitely many primes to actually occur at Dehn surgery points.
I see.
So that's something we'd like to prove. There is an almost converse to the statement that, you know, if the condition star is satisfied, it's not quite true, but if the Alexander polynomial has no multiple roots, then we can get, and the Azumaya, yeah, then you can get the converse.
More questions? It seems to be the case, so thank Alan again. So now we have tea break and we resume.